Okay, so in the last class, we were trying to solve problems using the KKT conditions, right? So, trying to come up with a general framework for solving constrained optimization problems, primarily convex constrained optimization problems, but in general, they could be non-convex as well. And we were operating under this framework of strong duality. So, whatever, as long as strong duality is guaranteed, we want some approach to solve the constrained optimization problem. And one approach that I outlined was using these KKT conditions. So instead of trying to come up with a numerical approach to solving the the constrained optimization problem, you try to solve for a set of conditions. So you are given a bunch of equations, which could be nonlinear equations, and you try to find a solution to these system of equations. If you can come up with a solution, then hopefully you end up with a solution to your constrained optimization problem. All right? And the system of equations that you get come from these so-called KKT conditions. So first it's primal feasibility, that is all of the primal constraints have to be satisfied. And dual feasibility, that the dual variables lambda 1 through lambda n, they should all be greater than or equal to 0. And we have this stationarity, which says that the gradient of the Lagrangian with respect to x evaluated at this point x star, lambda star, mu star, that should be equal to 0. So it's a stationary point of the Lagrangian. And we have this complementary slackness condition, which says that for each inequality constraint, either the corresponding Lagrange multiplier should be equal to 0, or that constraint is satisfied with equality. One of these two things must happen. It can't be that both of the variables are simultaneously slack. So you can't have lambda greater than 0 and fi of x less than 0. Okay? And I made this point that if the primal optimization problem satisfies strong duality, then the KKT conditions are necessary. They're not sufficient. But in addition, if the problem is convex, then the KKT conditions are also sufficient. So if someone presents you a constrained convex optimization problem, then the first thing you should try to do is try to solve for the KKT conditions. If it works and you can get a closed form solution, then you're done. You don't have to look any further. If not, then you have to try to think about other numerical approaches to solving the problem. All right? So we saw a couple of examples. One was this general quadratic problem with linear constraints, and we sort of saw that this can be solved by solving just a system of linear equations. So even though the objective function is quadratic and the constraints are linear, the ultimate solution can be obtained by solving some system of linear equations. Okay? And the other example that I was not able to fully complete in the previous class was this problem of trying to allocate power to various sub-channels in order to maximize the rate. So in this case, we had an optimization problem of the following form, where we wanted to maximize this objective function, which is summation I equal to 1 to k log 1 plus pi by sigma I square. The sigma I squares are all parameters that are given to you, and the primal variables are p1, p2, p3 up to pk. And this has to satisfy a power constraint, a total power constraint. So the summation of the pi's should be equal to some capital P. And each pi should be non-negative because it physically signifies how much power you are going to use in that specific sub-channel. All right? And the approach was the following. We first formulated this in standard form. It's as a minimization problem. We stared at it and saw that it's indeed a convex optimization problem. It also satisfies Slater's condition. So therefore, the problem is strongly dual. And for this, we first formulated the Lagrangian and then checked for each of the KKT conditions. So primal feasibility says that the total power constraint should be less than or equal to P, each of the powers should be greater than or equal to 0, and we only have inequality constraints over here. So we have a total of k plus 1 Lagrange multipliers, and each of these should be greater than or equal to 0. And then we also evaluated the gradient. We set the gradient to be equal to 0, based on which we got this constraint, this relationship between pi star, lambda star, and lambda I star. All right. So pi star, we saw for it to be, again, remember these are necessary conditions. So if you have a solution, then the solution must satisfy pi star equal to 1 by lambda star minus lambda I star minus sigma I square. All right. Now, based on the complementary slackness condition, we saw that, okay, you have a bunch of Lagrange multipliers. So in each case, either lambda I should be equal to 0 or pi star should be equal to 0. And similarly, either lambda star should be equal to 0 or the total power should be equal to p. And just with some basic observations, we saw that lambda star cannot be equal to 0, otherwise each pi star would be negative. So the only thing that can happen is the total power should be exactly equal to p, and which is kind of natural to expect, because if you have additional power, you may only, it makes sense to use it in some specific subchannel instead of just leaving it to waste. All right, so we handled one of those. So now we know that lambda star is equal to 0, which kind of eliminated one variable. Now the next, again, we looked at the other complementary slackness condition. So if lambda I star is equal to 0, then pi star must be equal to 1 by lambda star minus sigma I square. And if lambda I star is not equal to 0, then pi star must be equal to 0. And under this condition, we sort of simplified to see that in this case, sigma I square is greater than or equal to 1 by lambda star. So if this happens, then pi star should be equal to 0. So effectively, if you have too much noise in one specific subchannel, then you don't allocate power to it. Because it's too noisy, it's wasteful to allocate power to that subchannel. Okay? But all this says is, I still haven't completed the solution yet, because, okay, what is lambda star? It's still a variable that I have not determined yet. Right? Okay. So remember that lambda star is not equal to 0. All right. So if lambda I star, if sigma I square is greater than 1 by lambda star, then pi star is equal to 0. If pi star is non-zero, then it must be equal to 1 by lambda star minus sigma I square. So basically what this is saying is that the power that you allocate to each subchannel is always going to be, it's going to be 1 by lambda star minus sigma I square if sigma I square is less than 1 by lambda star, and it's equal to 0 if sigma I square is greater than or equal to 1 by lambda star. So let me sort of summarize that. So pi star, this is equal to 1 by lambda star minus sigma I square if sigma I square is greater than 1 by lambda star, and it's equal to 0 else. Right? The second part I got from here, and the first part I got from here, just by analyzing the corresponding complementary slackness conditions and some of the others. So in other words, this is just equal to the positive part of 1 by lambda star minus sigma I square. Okay, so this notation denotes exactly this. So it's equal to this if the quantity is positive and it's equal to 0 otherwise. Now, how do you find lambda star? Correct. We have the total power constraint. We know that based on the KKT conditions, summation I equal to 1 to k, Pi should exactly be equal to P. So this implies that 1 by lambda star minus sigma I square, the positive part, when summed over all subchannels I, this should be equal to P. Now I can't get a closed form expression for lambda star over here because ultimately this is the positive part. I don't know which ones are positive or not, but that doesn't matter. It's just maybe one line of code that I can numerically solve for lambda star very easily, right? But what is interesting about this is sort of the physical interpretation of this particular solution. All right. So I can view this in the following way. So I have a number of subchannels. I have subchannel 1, subchannel 2, subchannel 3, up to subchannel k. In each subchannel, I can think of these levels. So there's already a certain level of noise, and I want to decide what is the level of power that I want to allocate to this specific subchannel. All right, so the level in subchannel 1 is sigma 1 square. In subchannel 2, it is maybe sigma 2 square, which is larger than sigma 1 square. In subchannel 3, maybe it's at a much lower level, sigma 3 square, and so on. Maybe subchannel k, it's very high, sigma k square. And what is the total power that I'm going to allocate to each subchannel? I set a threshold, which is 1 by lambda star. Lambda star. And the amount of power that I allocate is how much you have below this particular level. All right. So this is going to be P1, this is going to be P2, and Pk is going to be equal to 0. Right? Because I want P1 is equal to 1 by lambda star minus sigma 1 square. Right? 1 by lambda star minus sigma 1 square. And P2 is equal to 1 by lambda star minus sigma 2 square, and so on and so forth. So you can think of this as though you have a tank, all right, and you have a certain level of water, which is 1 by lambda star. And you have these steps, right, sigma 1 square, sigma 2 square, sigma 3 square, and so on. And once you fill in water, some of these steps could come above the water, some of these steps are below the water level. And what is the height of, or what is the depth of the step from the water level? That's the amount of power that you are going to allocate. So this is commonly referred to as a water filling argument. All right, and this is also called the water filling solution. Right. So this is a nice example where if you looked at the original, I'm sorry, yeah, yes please. Yeah.
Intuitively it looks like you may want to do more with sigma 3 squared, right?
Correct.
So does it make sense to put these guys in an increasing order and then do your water filling?
It doesn't matter.
Generality, right?
You don't lose any generality, true. Yeah.
No, but even this way you are at the optimal?
It doesn't matter, right? So it's completely independent of the ordering of the sigma 1 square, sigma 2 square, and so on. Yeah. there's absolutely no generality. Yeah, maybe if I had ordered them, then it would have looked much nicer. In fact, you're right. But again, the order does not matter. The solution still remains the same. Okay. Yeah. So the primal problem was a pretty complicated looking problem, right? And there was no way to easily guess the solution. You can't just rely purely on intuition to say, oh, this must be the solution, or you can't get it by geometric means. But the KKT conditions give a nice, just allow you to find the solution nicely in this case. All right. I have almost a closed form expression, but it's good enough, right? The complexity of solving this is negligible. Any questions? Okay, so now we know how to solve, at least using given the KKT conditions. We know how to look for a solution to the constrained optimization problem. But where do these KKT conditions come from? Why is it that if I solve for the KKT conditions, I'm actually arriving at the solution to the constrained optimization problem, right? So let's view that, and that also has a nice sort of geometric interpretation in terms of how the Lagrangian behaves. In particular, the complementary slackness condition seems to have appeared out of nowhere. Right? The first two conditions, the primal and dual feasibility constraints, it's there. There's nothing special about them. The fact that the Lagrangian, the gradient of the Lagrangian should be equal to 0, that is also a bit surprising, because somehow we seem to have eliminated the constraints. Because when we're evaluating the Lagrangian, the gradient of the Lagrangian and setting it equal to 0, this is as though it's a global minimum, right? We're looking for a global minimum. Or in fact, it's just a local minimum, because I'm saying that these are necessary conditions. But there's no intuition whatsoever so far for the complementary slackness conditions. Why is it the case that either lambda I star should be equal to 0 or fi of x star should be equal to 0? Right? So we look at that, but there's a question.
Again, the previous case, it really depends on 1 by lambda star, how we fix that.
Correct, that is true.
For that, we need to have info for maximum noise flow.
So you need to have information about all of the sigma I squares.
To decide this 1 by lambda star, what the maximum noise flow?
No. So you need all of this, right? So you choose 1 by lambda star based on this condition. The sum of all of these terms should be exactly equal to P. All right. So for example, if P is equal to, say, 3, all right, take a toy example where P is equal to 3, sigma 1 star is 1, sigma 2 star is equal to, say, 5, and sigma 3 star is also equal to 1. All right. Then I would want, let's maybe do that little example first. So P equals 3. sigma 1 star equal to 1, sigma 2 star is 5, and sigma 3 star is equal to 1. Then what I want is 1 by lambda star minus 1 plus 1 by lambda star minus 5, 1 by lambda star minus 1 plus should be equal to 3. Can you guess what 1 by lambda star should be equal to? Yeah, 2.5. And how did you get that? Correct. So the guess is that both the first, this last term, the second term would be equal to 0, because there's anyway you don't have enough to satisfy. So essentially you get 2 times 1 by lambda star minus 1 plus, which is this 1 by lambda star, should be equal to 3. Right? Or 1 by lambda star is 1 plus 3 by 2, which is 2.5. All right? Okay. Any other questions? It's lambda I star. Sorry, 1 by lambda star. Correct. Okay, I'm sorry. I should have said that these are sigma 1 square, sigma 2 square, and sigma 3 square.
Why do you remove the middle terms?
So again, it was sort of a guess in this case, but you can try to numerically solve for it. But in general, if I chose, suppose that 1 by lambda star is greater than 5. All right, it's greater than 5. If 1 by lambda star is greater than 5, then what is 1 by lambda star minus 1 plus 1 by lambda star minus 1? What would it be? So 1 by lambda star is greater than 5. So 1 by lambda star minus 1 would be at least 4. Right? This contributes 4. This also contributes 4, which is much more than 3. All right? So one way is to sort of go sequentially, you sort them in ascending order and see how much water you can fill in some sense. All right? But it's easy to just come up with a routine because there are only k terms in this particular summation. You have to just decide which of these k terms can be 0 and which of the k terms should be greater than 0. All right. Any other questions? Okay. So again, maybe I won't give all of the details, but we'll still see how we get the KKT conditions from just strong duality. So our basic assumption is that strong duality holds. We'll first see how the KKT, the complementary slackness conditions just come about. All right. So let's start with the following quantity. So we are assuming that strong duality holds. So in other words, P P star is equal to D star. All right. By definition, what is P star? It is equal to f of x star. So we're assuming that x star is the constrained minimizer for our primal optimization problem. And D star is equal to G of lambda star nu star, where lambda star nu star are the solutions or the optimizers for the constrained dual optimization problem. All right. So let's write down this G of lambda star nu star in detail. So how did we get G in the first place? We did it by minimizing L of x lambda nu with respect to x, all x, not just constrained over the set of feasible points. So this is equal to the infimum over all x in the domain of L of x lambda star nu star, but let me just write that down explicitly. F of x plus summation over I lambda I fi of x plus summation j equal to 1 to m mu I nu j h j of x. Correct? Okay. Now the right hand side is the infimum over all possible x. If I plug in one particular value of x, then this quantity is going to be less than or equal, this is going to be greater than or equal to the infimum. Right? I have the Lagrangian, the minimum of the Lagrangian over all x gives me G of lambda star nu star. For a specific choice of x, the value of the Lagrangian can only be greater. It can only be greater than G of lambda star nu star. In particular, if I plug in x star, which is the solution to the constrained primal problem, then this is less than or equal to f of x star plus summation I equal to 1 to n lambda I fi of, I should say lambda I star nu I star plus summation j equal to 1 to m mu j star hj of x star. Okay, is this step clear? Okay, good. So now what can I say about, again, x star, remember, is the solution to the constrained optimization problem, the primal objective. What can I say about this particular quantity? It should be equal to 0 because x star satisfies all of the constraints. Right? So this quantity, this is 0. What can I say about this particular quantity? It is greater than or equal to 0. This quantity is greater than or equal to 0. Right? So have f of x star less than or equal to f of x star plus something that is, I'm sorry. This should be less than or equal to 0. Right? So have f of x star which is less than or equal to f of x star plus something that is less than or equal to 0. Right? x star. I'm sorry. I'm sorry. It's greater than or equal.
The other one,
Which one?
the left, the one between F and C.
The one between f and because what are the assumptions? So x star satisfies all of the constraints, right? So what can you say about fi of x star?
Should be
Less than or equal to 0. And what about lambda I star?
not that one, the other one, to the left of that.
Oh, this one. Because this is an infimum, right? So this is so the objective function is the same. This is the Lagrangian, right? But above, this is the infimum of the Lagrangian over all possible x.
What is X star again? It's the
X star is the constrained optimum for the primal problem,
yeah.
right? It is some specific x star. Okay, it doesn't matter what, I could plug in any other x I want over here, right? Because this is the minimum over all possible x in the domain. For any specific x, the value of the Lagrangian can only be greater than or equal to this quantity. Is that okay?
So by transitioning from G of lambda star to gamma star to the infimum part, like why are we fixing this lambda and gamma? Because it's infimum, right? So like, should we already fix that?
So I'm looking at G evaluated at lambda star nu star, right? So for every choice of lambda comma nu, G of lambda comma nu is the infimum of this quantity taken over all possible x. The infimum is only over x. It's not over lambda star nu star, over lambda or nu, right?
But like previously when we used to solve for lambda and gamma.
Correct. We used to do that. That's true. But right now I'm fixing this nu and
So this lambda star and mu star, are they the optimizers or just like are
they are the optimizers. But again, it is not particularly important in this context, right? Because G of lambda star nu star achieves D star. That's the assumption. So obviously this is obtained by maximizing G of lambda comma nu over all possible lambda greater than or equal to 0 and nu in RD, right? But at least for this line of arguments, that's not important. All that matters is that lambda is greater than or equal to 0 and nu is anything arbitrary. All right? Okay, so essentially what we have is f of x star is less than or equal to f of x star plus something that is non-positive. So can this non-positive quantity be negative? It can't, right? So this whole quantity must be equal to the quantity that is shaded in pink. It should be equal to 0. Should be equal to 0 for all I, and which means that, this should be equal to 0, which can only happen if lambda I star fi of x star, this is equal to 0 for all I, because each one of them is non-positive. All of them have the same sign. Yeah, question?
The gradient is zero because the second and third steps.
I'm sorry, gradient? We haven't talked anything about the gradient so far.
Stationary.
That is there, but I'm not worried about that right now. All right. Again, all of this happened purely because I assumed that P star is equal to D star. That is, f of x star is equal to g of lambda star nu star. If this happens, then this must happen. It's a necessary condition. Yeah.
While each term should be 0.
Simple thing is that all of these have the same sign. Right? Each of these terms has the same sign. Each one of these is less than or equal to 0. And the sum should be equal to 0. So if even one of them is negative, then the sum can never be equal to 0 because there are no positive terms in this summation. Questions? Okay, so this is how we arrived at the complementary slackness conditions. Okay. Now let's look at the other case. So where do the stationarity conditions come from? All right. Now let's consider a x star, lambda star, mu star. All right. Remember that x star is the solution of the primal optimization problem, extended optimization problem. Lambda star, mu star are solutions of the dual optimization problem. So let's look at lambda star, mu star. So G of lambda star, mu star is equal to the infimum overall. Let me write it in the following way. It's equal to the supremum over all lambda greater than or equal to 0 mu star in Rm of the infimum x in the domain of L of x lambda mu. Correct? Now, if I didn't have any of these constraints, then I didn't have a problem. If I set the gradient of L to be equal to 0, then x star, lambda star, nu star should be a solution to the gradient being equal to 0. But these are constrained. Each of these have their own set of constraints. Right? So in general, I can't simply take the gradient, set it equal to 0 and hope to arrive at x star, lambda star and mu star. Because we have constraints over here. We can't just ignore them arbitrarily. But something interesting happens. So let me try to sort of reverse the supremum and the infimum. All right. Let's take L of x lambda and nu and try to first maximize with respect to lambda and nu. All right. So consider some arbitrary x that belongs to the domain. It may satisfy the constraints, it may not satisfy the constraints, doesn't matter. But let's start with an x and look at the supremum over all lambda greater than or equal to 0 and nu in Rm of L of x lambda and nu, but let me sort of expand it out because it will be helpful. This is f of x plus summation over I lambda I fi of x plus summation over j nu j Hj of x. Okay, so I take an arbitrary lambda and nu. I take an arbitrary x and try to maximize this whole quantity with respect to lambda and nu. Now suppose that x satisfies the constraints. All right. Then suppose that x satisfies the constraints, then what happens to this supremum? Or maybe let me start with the other way around. So suppose x does not satisfy the constraints. So x is not feasible. Then what is the above supremum going to be equal to? So when I say x is not feasible, it means that either there is some I for which fi of x is greater than 0, strictly greater than 0, implies there exists I such that fi of x is strictly greater than 0, or there is some j such that hj of x is not equal to 0. Okay. So what can you say about this supremum? For a given x. Why? Correct. Correct. You can make lambda I arbitrarily large, and this whole supremum can be, or this whole function can be arbitrarily large. So it's an increasing function of lambda I, right? And it's unbounded. So this is if fi of x is greater than 0, then it's infinity. Similarly, if hj of x is not equal to 0, if it's positive, then if you increase nu j, then it grows unbounded. If hj of x is negative, then you decrease nu j up to minus infinity, this whole thing goes to plus infinity. So the supremum is equal to plus infinity if any of the constraints are not satisfied. If x is not feasible. Okay. So that is if x is not feasible. Now if x is feasible, then, well, we can get rid of this particular part, because if x is feasible, then hj of x is equal to 0 for all j, so this whole quantity is not present. Get rid of it. But we have this term to take care of. What can you say? So if x is feasible, what can you say about each fi of x? It is less than or equal to 0. Lambda I fi of x can only be less than or equal to 0. So this whole quantity can only be less than or equal to 0. And this is the only quantity that depends on lambda. What is the maximum over all lambda greater than or equal to 0 of this? It's equal to 0, right? Because if any of the lambda i's are non-zero, or it's possible to have some of the lambda i's to be non-zero and all of these to be equal to, and these to be strictly negative, right? So the maximum of this, or the supremum of this whole quantity over all lambda greater than or equal to 0 is just f of x. Alright, so that's nice, because it means that if I look at this particular function, if I look at this particular function, now this is a function of x, right? The quantity on the left is a function of x because I've taken the supremum with respect to lambda and nu and I've got rid of those. So this function has the behavior that it's equal to f of x for all feasible points and it's equal to infinity for all points that are not feasible. So now if I look at the unconstrained minimum of this function, what do I get? What is
Minimum of
infimum over all x in the domain of supremum lambda greater than or equal to 0 nu in Rm of L of x lambda nu. What is this equal to?
fx star.
It's f of x star. And in fact, so one thing is that this is equal to f of x star. That's number one. So this is equal to p star, which is also equal to d star if strong duality holds. But there's something else. What can you say about the minimizer of this inf sup of this?
It's feasible.
I can just use usual calculus.
No, nothing, no calculus, nothing is required. So I have this function, right? Basically, how did I get this? I took the minimum of this. I first took the supremum and then took the minimum over all x, right? So at what x is this infimum achieved?
Is it convex? Convex and the
It's equal to x star, right? Right? Which is the x star that you get by solving the constrained optimization problem. Correct? So in fact, the minimum, so this infimum is achieved at x star. It's a subtle point, but what is important to note is that
Is it x star only or
so if this problem is convex, then only at x star, right? If not, there could be multiple solutions, right? Because in principle, there may not be even for the constrained optimization problem, there may or may not be a unique minimizer. Okay, but in any case, so if the x star or okay, well, I should let me reword this to be clear. X star achieves this. Alright, there may be some other point that also achieves this infimum, but definitely x star achieves this infimum. Okay, but the point to note is that what we did over here was an unconstrained minimization, not a constrained minimization. Of course, this ended up being an extended value function, so that unconstrained minimization was equivalent to the constrained minimization. But the nice thing is that if I take inf and then sup of this, then the unconstrained minimizer is equal to the constrained minimizer. Right? Which is also equal to the supremum lambda greater than or equal to 0 nu in Rm of the infimum over lambda greater than, over all x in Rm or x in the domain of L of x lambda.
you can only flip when the sup inside is finite, right?
Which one?
basically flip the infant soup here.
I flipped the inference, so, but I showed that the same, right? Because I know that if I have strong duality, okay, if I have strong duality, then the right hand side, this quantity is equal to d star. This is anyway equal to d star, which is also equal to p star, if I have strong duality, which is also equal to this,
Which you proven.
which I have proven. The one subtle point, I guess what you're confused is,
Does the second part need strong duality?
which one?
In the first part, does it need strong duality?
This part requires strong duality, right?
The other part.
The other one, not really. Right? I've never used strong duality anywhere over here. So this is true. Always.
No, what I'm not able to get is how is this different from the definition of strong duality?
Which one?
The right side, RHS in this.
This is I get it purely by strong duality. I've done nothing else.
Okay, so you just plug in the definition.
I've just plugged in the definition of strong duality, nothing else. It's only that this required a little more analysis. That is all. Okay. But the only point I wanted to make over here is that this inf and sup can be exchanged. Exchanging the inf and sup doesn't change what we have. Okay. So you're taking the supremum with respect to one and infimum with respect to some other set of variables. So this effectively, the solution is effectively a saddle point. All right.
Does the left part help us computationally?
The left part is exactly what helps us computationally. And the reason is that because this is a saddle point and this is obtained as an infimum, right? So if x star achieves this, then x star should be a stationary point of this particular function. All right, directly from this, I get that x star, so basically x star must be a stationary point of L of x lambda nu. It's again a necessary condition. It's not sufficient, it's necessary. Okay? Purely because x star should be a stationary point for this particular min-max problem. Which one? Correct. So those are the two KKT conditions that were non-trivial. One, that x star should be a stationary point of the Lagrangian, x star of Lagrangian at lambda star nu star, and the second is the complementary slackness conditions.
You could have proved this above itself when you do complements. So you have infimum of x belongs to D and the
Correct.
is equal to f of x star,
It is equal to f of x star. I agree.
which means you're taking the gradient of relation.
I agree, but I basically wanted to. I sort of elaborated on this. That's effectively what I did again. But I also wanted to show you that if you first take the supremum with respect to lambda and nu, then you just end up with with this particular function over here. that you can see this more naturally. Right? Any questions? Okay, so
So how does it work? Is it like you select a point in the feasible set arbitrarily and then you optimize lambda?
which one?
The how do you do it in story?
I don't care about how I do it computationally, right? I just wanted to end up with the fact that I wanted to make 2 points over here. One is that if I first take the supremum with respect to lambda and nu, then I get the extended value function corresponding to the constrained optimization problem. Right? So it's equal to f of x if x satisfies the constraints, and it's equal to infinity otherwise. And therefore, the unconstrained minimization of this particular function gives me the constrained minimizer. All right. I don't care about how I evaluate this, because in the end I only want to arrive at this necessary condition that x star is a stationary point.
You can also sort of see status transition from here. If there's an x such that fi of x is strictly less than 0,
Correct.
it forces your lambda to be 0.
It forces your lambda to be equal to 0, yes. Yeah. So in fact, using this I derived a necessary condition, but using a similar approach and also using the fact that f is convex, you can also arrive at the corresponding sufficient conditions for optimality. Right?
So why do you call this unconstrained? You still have that lambda term is greater than 0, right?
It is, right?
Still a constraint, right?
That's okay. But I'm only interested in how it behaves with respect to x.
Oh, okay.
Because I'm only setting the gradient of L with respect to x and setting that equal to 0. Because setting the gradient of L with respect to lambda or nu doesn't give me anything interesting. Right? In fact, the gradient with respect to lambda need not be equal to 0. Because if you see the gradient of lambda, if you take the partial derivative of the Lagrangian with respect to lambda I and set it equal to 0, effectively what you get is fi of x is equal to 0, which may not happen. Right? Because lambda is not going to be an unconstrained minimizer of the objective function. It's not necessarily so lambda star is not necessarily a stationary point of the Lagrangian. Right? X star is a stationary point of the Lagrangian. Yes. That's something special about X star. Okay. So now I want to sort of go back a little bit, back to duality, and introduce this idea of the conjugate of a particular function. That was also there in your homework. But the conjugate is something that arises naturally when you're talking about optimization problem with linear constraints. So let's recall the definition of the conjugate. So you're given some function f and you define f star of y to be equal to the supremum over all x in the domain of f of x transpose y or y transpose x minus f of x. For many functions of interest, you can compute the conjugate. All right. There are other interesting places where the conjugate kind of arises naturally. For instance, if what you can show is that if you've seen Chernoff bounds, you can express the optimal Chernoff bound as e to the conjugate of the log moment generating function. All right. There are many other problems in math where the conjugate naturally arises, and therefore there are a lot of people who have actively studied the conjugate of a function. But in our context, the conjugate is helps because if you can compute the conjugate, then you can also compute the dual of many optimization problems. All right. So let's consider the following optimization problem. Let's say you want to minimize some function f of x subject to some inequality constraints, linear inequality or affine constraints less than or equal to b, and say gx equal to h. Okay, as long as you have affine constraints, you can always set it up in this particular form. So in other words, your constraint set is a polyhedron. Let's try to compute the dual of this particular thing. So the Lagrangian, so first x lambda nu, this is going to be equal to f of x plus, I can write this as lambda transpose ax minus b plus nu transpose gx minus h. Okay, and I want to take the infimum of this with respect to all x in the domain. So g of lambda comma nu is the infimum of the entire right hand side, but maybe even before I do that, let me simplify the right hand side just a little bit. I want to show that g of lambda comma nu can be expressed as a function of the conjugate of f in some way. So I want to first bring the Lagrangian in a form that looks similar to, say, something transpose x minus f of x. So first let's collect all of the terms that don't involve x at all, and all of those terms which are linear in x, and then the rest of the terms. Okay, so firstly, lambda transpose b doesn't depend on x, nu transpose h does not depend on x. So let's bring them out. Minus lambda transpose b minus nu transpose h. And then I want to express the rest as something transpose x plus this quantity is nothing but A transpose lambda, the whole transpose x, and this quantity is G transpose nu whole transpose x. So in fact, let me just skip a step, say that this is A transpose lambda plus G transpose nu transpose x plus f of x. Okay, so G of the Lagrange dual at lambda comma nu. This is equal to, well, the first two terms don't depend on x at all, so you can just take them out. It's p minus nu transpose h plus infimum over all x in the domain of A transpose lambda plus G transpose nu transpose x plus f of x. To express this as a conjugate, I have to express it as supremum of something minus f of x. Right? So this is equal to minus lambda transpose B minus nu transpose H minus supremum x in D. I just introduced two negative signs, one before the supremum and one after, minus A transpose lambda minus G transpose nu transpose x minus f of x. Right? Okay, so this is minus lambda transpose B minus nu transpose H. What is the whole supremum term going to be equal to? So again, if it helps. In terms of f star. Can you write this whole quantity as f star of something?
Star is some of the
So I have defined f star. No. F star is the conjugate, right? So can I express this whole quantity as the conjugate of f evaluated at some point? Correct. It is just f star of this particular quantity. Right? This is f star of minus A transpose lambda minus G transpose nu. And so if you can find the conjugate, then you can also very easily find the dual of any affine constrained optimization problem. Questions?
Even after this, you will have to do a constraint optimization.
Correct. It doesn't help. It doesn't significantly help us in solving the problem as such, but it helps you evaluate the dual optim. So, okay. Later on, we'll see a number of examples where solving or finding the dual optimization problem does not necessarily help us solve the primal optimization problem. but it gives us a lot of insight as to how the solution should behave. It gives us, for example, it could be geometric, it could get some sort of a geometric interpretation of the optimal solution, or and so on and so forth. In one case, we'll see the example of linear classifiers, more specifically support vector machines, and we'll see what the support vectors correspond to in terms of the dual of the primal optimization problem that we'll try to solve. So duality as a tool is much more powerful than just solving the optimization problem. Sometimes you're not able to get a closed form expression for the solution, but then you can infer a lot about the properties of the solution even without solving it. For example, through the dual. At times, the dual is sometimes easier to solve than the primal optimization problem because it looks more like a standard form. Sometimes the dual problem can look like a standard optimization problem. For example, something like quadratic with quadratic constraints and so on. For instance, let's see. So in one of the problems, sort of almost trivial problems that we had, yeah. So in this particular case, we had this primal optimization problem, which was quadratic with quadratic constraints. The dual optimization problem involved something that was not just quadratic. It was something quadratic divided by 1 plus lambda, something quadratic over linear, right? So in this case, the dual didn't help us solve the primal. But suppose your actual primal problem looked something like this, and you wanted to compute the dual of this optimization problem, that would end up being a quadratic problem with quadratic constraints, for which there are already standard tools to solve.
The dual of the dual is the primal.
So that's another point. The dual of the dual is the primal. Not always, but if strong duality holds, then the dual of the dual is the primal. And can you tell me why?
Because you have the primal problem and the dual problem. We have the
Correct.
same solution.
Correct, they have the same solution.
So I can take the dual on both sides. So
Yes.
it would have the
In a sense, yes. Again, it's not a proof, but you see why the dual of the dual should be a primal. In fact, an exercise for at least some of the examples that we've seen so far. For example, the linear program or even quadratic program with, say, linear constraints. Compute the dual and compute the dual of the dual. You should arrive at the primal problem. Any other questions? Okay, so just as an exercise, let's try to find the conjugate of a couple of simple functions. So suppose that f of x is a times x plus b. What is the conjugate equal to? F star of y is the supremum over all x in, say, Rd of y transpose x minus ax minus b. I'm sorry, this should have been some A transpose x minus b. What is this equal to? Yeah?
minus b.
Is it always equal to infinity?
When y is a, it is
When y is equal to a, it is minus b, and if y is not equal to a, it is plus infinity, right? So this is equal to infinity if y is not equal to a, and it's equal to minus b if y is equal to a. Good. Right. Let's take another example. Question, yeah.
So this is like, so at only one point it is minus b, else it
Correct.
is.
Yeah. Let's take f of x is equal to, so let's say ax square plus bx plus c, single variable. Yeah. What is the supremum going to be equal to?
when y is minus b.
When y is minus b, okay, does it matter? Sorry?
When y is minus b.
Okay. I have that ax square term, right? In fact, in this case, the value of y doesn't matter at all. You have to be very careful. Yeah, yeah,
A is positive,
correct,
then you have a maximum.
correct.
So it will be minus c.
It will be equal to what you said the derivative. Take the derivative, set it equal to 0, and you get a solution. And so, if a is greater than 0, then this is a concave function that is bounded from above. So you can take the derivative, set equal to 0, and find the supremum. Right? What if a is not greater than 0? Then it's equal to plus infinity. Right? So in the first case, a is, let's say, less than 0. F star of y is infinity for all y. The second case is when a is greater than 0. So you can find f star of y. Again, it's an easy exercise, so you can find f star of y is going to be finite. For all y. This is the third case. What if a is equal to 0? Then you again end up with a linear function. Then what you said makes sense. So it's defined, so it's only when y is equal to minus b that this quantity is finite. only if y is equal to minus b. So when we're talking about conjugates, you have to be careful. All right. Okay, so I think this is a good time to stop.